Good evening everybody. I welcome you all to my third lecture on network synthesis. In my previous two lectures, we have seen the introduction regarding network synthesis as well as in detail procedure how to synthesize a given impedance RL function. In today's lecture, we shall see the in detail process of how to synthesize a given RC impedance function using both Foster as well as cover forms. So let us consider an example. Z of s is equal to s plus 1 into s plus 4 divided by s into s plus 2. So first let us check whether this is an RC impedance function. So I draw a pole 0 plot. +1, -2, -3 and -4 and origin. So we have a pole at 0 and -2. We have a 0 at -1 and -4. So as you can observe that we have a pole near origin. So this is an RC function. So the first method is Foster first form. So here you can observe that both the numerator degree and denominator degree are same. So upon multiplication, this is s square plus 5s plus 4 and this is s square plus 2s. So both have the same degree. So now I will divide both numerator and denominator once. So s square plus 2s, s square plus 5s plus 4. This goes once and s square plus 2s. So this is 3s plus 4. So the remainder is positive. So the given impedance function I can write as 1 plus 3s plus 4 divided by s square plus 2s. So that is s into s plus 2. This I can consider as z1 of s plus z2 of s. Since z1 of s is a constant, so directly we have got the first element, which is r1 is equal to 1. So consider z2 of s, which is 3s plus 4 by s into s plus 2. So upon partial fractions, it is a by s plus b by s plus 2. So as we know, a is obtained by writing the entire expression except s. So it is 3s plus 4 by s plus 2, substituting s is equal to 0. So when I substitute s is equal to 0, I will get a value as 2. So b is equal to, so except s plus 2, write the entire expression s plus 4 divided by s and substitute s is equal to -2. Then we'll get the b value as 1. So this I can write as 2 by s plus 1 by s plus 2. So the total impedance function z of s is nothing but 1 plus a value is 2, so 2 by s, and b value is 1 by s plus 2. So this is nothing but z1 of s plus z2 of s plus z3 of s. Since we have considered this term as z2, okay, you can consider this as z2 dash and z2 double dash. Okay. Since we have considered this entire as z2. So as you know, the general format, if the network is all the impedances are connected in series. So instead of z1, I have a resistor. So z2 dash is nothing but 2 by S. So it is in the form of 1 by CS. So from this I can say that the capacitor value is 1 by 2 farads. The third term, so it is neither in the form of, that is Z2 double dash, it is 1 by S plus 2. This is neither in the form of R, neither in the form of LS, neither in the form of 1 by CS. So it means that is the parallel combination of R and C. So in such case we have to make numerator as 1, but in this case already the numerator is 1, so this I can write as y double 2 dash S. So in admittance these two terms are being added. So in admittance form we know that constant represents G, inductor represents 1 by LS, and capacitor represents CS. So this indicates 2 indicates G, so implies R2 value is 1 by 2 ohms. S indicates CS or C2S, so C2 value is 1 farads. So instead of Z1 we have a resistor of 1 ohm. Instead of Z2 dash I have a capacitor of 1 by 2 farads, and instead of Z2 double dash I have a parallel combination of resistor 1 by 2 ohms and capacitor 1 farads. So the network that I obtain is, first element is a resistor, second element is a capacitor of value 1 by 2 farads, and the third one is a parallel combination of R and C. R value is 1 by 2 ohms and C value is 1 farads. So this is the network obtained by synthesizing an RC impedance function using Foster first form. So then the second method is Foster second form. So in Foster second form we know that we should consider y of s. So y of s is equal to, so that's just interchange the numerator and denominator. So that is s into s plus 2 divided by s plus 1 into s plus 4. So even in this case the numerator degree and denominator degree are same, so we have to divide the numerator and denominator once. So this is nothing but s squared plus 2s, s squared plus 5s plus 4. So upon division of numerator and denominator once, s squared plus 5s plus 4, s squared plus 2s. This goes once, s squared plus 5s plus 4. So here in this case I get 3s minus 4. Since the remainder is negative, now I should consider y of s by s. That is nothing but s plus 2 into s plus 1 into s plus 4. Now this upon partial fractions becomes s a by s plus 1 plus b by s plus 4. So as you know, a is equal to, except s plus 1, consider the entire fraction, s plus 2 by s plus 4, substitute s is equal to minus 1, and b can be obtained, consider the entire expression except s plus 4, s plus 2 by s plus 1, and s is equal to minus 4. So a value is 1 by 3 and b value is 2 by 3. So 1 by 3 by s plus 1, 2 by 3 by s plus 4. So then y of s becomes 1 by 3 or s by 3 plus 1 and 2s by 3 by s plus 4. So this I can consider as y1 of s plus y2 of s. So these two terms are neither in the form of g, neither in the form of cs, or neither in the form of 1 by ls. So that means these two terms individually are parallel combination of r and c. So in such case we have to consider y1 of s, which is s by 3 by s plus 1. So the numerator should be made 1. So this I can write as 1 divided by 3 by s into s plus 1. So this is 1 divided by 3 plus 3 by s. So similarly y2 of s is nothing but 2s by 3 by s plus 4. So by making the numerator as 1, so this becomes 1 divided by 3 by 2s into s plus 4. So this is 1 by 3 by 2 plus 6 by s. So it is considered individual terms y1 of s. So we have obtained y1 to be 1 divided by 3 plus 3 by s, and y2 we have obtained as 1 divided by 3 by 2 plus 6 by s. So this I can write as 1 by z1, and this I can write as 1 by z2. So impedances are being added, so these two terms are in series, and here also impedances are being added, so these two terms are in series. So since this is impedance, it indicates R2 value is 3 ohms, and this is in the form of 1 by C1s. So this implies C1 value is 1 by 3 farads. Similarly, here also this constant indicates R2 value is 3 by 2 ohms. So this is in the form of 1 by C3s, which implies C3 value is 1 by 6 farads. So general notation of faster second form network is nothing but y1, y2. So instead of y1, I have a series combination of 3 ohms and 1 by 3 farads, and instead of y2 I have a series combination of 3 by 2 ohms and 1 by 6 farads. So the network obtained by synthesizing the given function using fastest second form is, so R value is 3 ohms and a capacitor 1 by 3 farads. Similarly, R 3 by 2 ohms and a capacitor 1 by 6 farads. So the third method is core first form. In core first form, we should consider z of s and write in the descending powers of s. So s square plus 5s plus 4 divided by s square plus 2s. and after writing both numerator and denominator in descending powers of s, we should apply continued fraction. So s square plus 2s, s square plus 5s plus 4. This goes once, so you'll get s square plus 2s. So this becomes 3s plus 4. So the remainder is positive, so this will be carried forward here. So here I have 3s, but I want here s square, so I multiply by s by 3. So you get s square and 4s by 3. So this will give you 2 by 3s. Since the remainder is positive, again this is carried forward here, 3s plus 4. Here I have 2 by 3s, but here I want 3s. So I have to multiply by 9 by 2. So this will give you 3s, and I will be left with 4. So again 2 by 3s. So in order to get 2 by 3s, I have to multiply here by s by 6, which will give me 3. So since this is done using impedance, this is Z1, this is Y1, this is Z2, this is Y2. Since Z is a constant, so for first element is a resistor R1. Here Y it is in the form of 1 by Cs. So C1 value is 1 by 3 farads. So here again impedance is a constant, so R2 is equal to 9 by 2 ohms. And here since again it is in the form of 1 by Cs, here C2 value is 1 by 6 farads. So the network obtained by synthesizing the given function using Core first form is, the first element is resistor, then here I will get a capacitor 1 by 3 farads, then the next element is 9 by 2 ohms resistor, the next element is a capacitor 1 by 6 farads. And the last fourth method is Core second form. Here both numerator and denominator must be written in ascending powers of s. So this becomes 4 plus 5s plus s square. The denominator becomes 2s plus s square. So applying continued fraction. So two s plus s square, 4 plus 5s plus s square. So here I have 2s, here I should get 4, so I should multiply by 2 by s. So I'll get 4 and here I'll get 2s. So this is 3s plus s square. Since the remainder is positive, this is carry forwarded here. Here I have 3s, I must get here 2s, so I'll multiply by 2 by 3. I'll get 2s here, I'll get 2 by 3 s square here. And this becomes 1 by 3 s square. Since remainder is positive, again this is carry forwarded here. Here I have s square by 3. Here I want 3s. So I'll multiply by 9 by s. this I'll get 3s square. So this is again carry forwarded here. I'll multiply by 1 by 3. So this is done in impedance. So this is Z1, Y1, Z2, Y2. Z1. So this is in the form of 1 by Cs. So the first element is a capacitor of value 1 by 2 farads. Admittance. Admittance is a constant. So this indicates G. So R1 value will be 3 by 2 ohms. Again, this is in the form of 1 by Cs. So C2 value will be 1 by 9 farads. And the last one, admittance, this indicates the value of G. So R value R3 is nothing but 3 ohms. So the network that we obtained by synthesizing the function, particular impedance function, using curved second form is first element capacitor 1 by 2 farads, second is a resistor of value 3 by 2 ohms, third value is again a capacitor of value 1 by 9 farads, and the fourth value is a resistor of value 3 ohms. So this is how we synthesize a given impedance function, particularly of RC type, using all 4 canonical forms. So that was the procedure how to synthesize a given impedance RC function using 4 canonical forms. In my next lecture, we are going to see how to synthesize in detail using 4 canonical forms of an impedance LC function. Thank you.